Good morning, everyone. My name is Tony Roskilly. I'm Chair of Energy Systems at Durham University. Thank you for attending the seminar today, and we've got some excellent speakers lined up for you. Durham Heat Hub is a joint project between Durham Energy Institute and Durham County Council to translate heat research to practical applications for the benefit of the community. And this is the 5th seminar in our series, exploring the challenges of decarbonisation of heat. This session is on heat storage, and part of the focus of the Durham Heat Hub is to ensure an transition to a net zero future. This particular subject for the seminar is really important to that transition. So this event is also supported by the new EPSRC research network on decarbonisation of heating and cooling, which is led by Durham and aims to disseminate heating and cooling research across to all stakeholders. Our first 2 speakers that I'll introduce are founder members of this network. During the presentations, please use the chat function to enter any question that you have for the speakers. We will look at those at the end of the session for the full panel at 11:30. If you could all stay muted until then, we'll run through the questions, but it might be that some of you might want to unmute and contribute and ask questions or make some points yourself. This session will be recorded and will be uploaded onto the Durham Heat Hub website and the Durham Energy Institute YouTube channel, and also on the Net Zero research website within the next few weeks. Links will be posted in the chat shortly. So again, thanks for your interest in previous seminars and this one, and hopefully in the future when we have more virtual sessions in 2021. Our first speaker is Huashan Bao. She's an assistant professor within Durham Energy Institute, and her presentation is on thermochemical energy storage. Huashan received her PhD from the Institute of Research and Cryogenics in Shanghai Jiaotong University in China. She worked as a research associate and then a senior RA in the Sir Joseph Swan Centre for Energy Research at Newcastle before a brief spell at Heriot-Watt University and then joining us at Durham University in 2019. Her main research is in thermochemical technology for heating, cooling, and energy storage and power generation. She is working on solar PVT collector, thermal energy storage, industrial waste heat recovery, and multi-energy systems and networks. So, Huashan, it's over to you.
Thank you, Tony. Good morning, everyone. Let me just share my screen. Yes, I'm Huashan Bao. I'm going to give a brief presentation on the advanced thermochemical sorption energy storage system that we're working on at Durham University. Thank you, Jackie, for this very festive drawback. It just really lightened up my mood. Okay, so as we know, thermal energy storage plays an important role in increasing the contribution of various types of renewable energies in the energy mix. It also can increase the efficiency of energy consumption by reusing industry waste heat. Various thermal energy storage technology and application exist. Compared to these 2 conventional thermal energy storage methods, sensible heat storage and latent heat storage, more compact thermal energy storage can be achieved by using sorption process and chemical reaction. The sorption heat storage can be divided into physisorption and chemisorption. the thermochemical heat storage without sorption, chemisorption, these two are classified as thermochemical storage. And compared to the, so these thermochemical storage take advantage of the strong chemical bonds to store energy as chemical potential, so that offers high energy density and also minimum energy loss due to the temperature independent means of storage. And compared to the thermochemical heat storage without sorption, the chemisorption cycle is typically driven by relatively lower temperature heat. So here is an example comparison between different storage methods. If to meet the daily meeting of a modern house with 100 square meter area, so we would need 2.3 cubic meter hot water tank, or we would need 1.5 cubic meter paraffin for a PCM storage system. If we use zeolite water physisorption storage system, it would require 0.7 cubic meter system. For chemisorption storage, it would require around 0.5 cubic meter system if we're using calcium chloride water as working pair, or 0.4 cubic meter system if we're using strontium chloride ammonia as the working pair. So in this example, the size of the chemisorption storage is almost only 1/6 of the size of the hot water tank required. Actually, the salt adsorbent packing density can be further increased. In that case, the system volume of the chemisorption storage can be further reduced. So the foundation of chemisorption process is the interaction between adsorbent and adsorbate. When the adsorbate changes from the adsorbed phase to gas phase, that's endothermic desorption, energy charging process. When the adsorbate comes into contact with the adsorbent from gas phase to the adsorbed state, and that release a lot of heat, and that's exothermic adsorption process, energy discharging process. If ammonia is used as the adsorbate, then the commonly used salt adsorbent like calcium chloride, strontium chloride, and manganese chloride. If water is used as the adsorbate, then the commonly used salt hydrates like magnesium chloride, strontium bromide, and magnesium sulfate. So this is the basic configuration of chemisorption storage system. SG bed contains solid adsorbent, which when it's supplied with heat, desorption takes place. The desorbed vapor condenses in the condenser. When desorption is finished, these two vessels are disconnected by closing the valve in between. So that's energy charging and storage. When there's a need for refrigeration, once the valve is open again, evaporation just happens spontaneously because of the temperature pressure between the two vessels. So the liquid in the evaporator extracts heat from surroundings and evaporates, and then absorbed by the SG bed, the adsorbent bed. So in this instance, adsorption heat needs to be removed in time, but actually in some cases, if the temperature of the adsorbent heat is high enough, that can be used for space heating. Then if there's a need for upgrading heat, then the evaporator is supplied with low temperature heat, and the adsorption heat is generated at high temperature, high pressure in the adsorbent bed, which is the useful high temperature heat output. A wide temperature range of heat output or cold output can be achieved by selecting the right salt adsorbent, and there are hundreds of options in terms of the salt adsorbent. In this PT diagram, we can see that the desorption happens at a higher temperature and higher pressure than the adsorption. For example, if we're using the chemisorption storage system for heat pump application, then in order to have the adsorption process to provide sufficient space heating at 60 to 80 degrees through radiator, then the sorption system typically require desorption temperature higher than 100 degrees. So the novel concept that we are researching, developing at Durham University is a hybrid storage system. A compressor expander are added into the basic configuration of the chemisorption storage system, a secondary solid adsorbent bed, that has relatively lower working pressure replace the condenser evaporator. Therefore, this hybrid system can store heat and electricity simultaneously. And because of the small amount of electricity input, it can effectively utilize the ultra-low-grade heat for desorption. The ultra-low-grade heat here refers to the heat at 40 to 70 degrees. Currently, fuel technology can't efficiently utilize ultra-low-grade heat, which represents the majority of the industry waste heat and renewable heat sources. For the energy discharging process, the stored energy can be flexibly generated in the form of heat or cold or electricity. And for this hybrid system, we have granted patents in USA and China, and to be granted in Europe very soon. So in this hybrid cycle, for example, if that use strontium chloride ammonia working pair, it runs like this. When the heat source temperature is high enough, let's say 110 degrees, it operates the normal sorption energy charging process. Compressor is bypassed. And when only ultra-low-grade heat is available, let's say 60 degrees, and it also can be used to drive the desorption process. However, at the same time, you will need help from the compressor to pressurize the desorbed ammonia so that the adsorption can effectively take place in the adsorber. So in this case, the compressor can be powered by renewables like wind turbines, solar PV. So both the ultra-low-grade heat and electricity can be stored in a system for later use. During energy discharging process, it can upgrade heat or produce cold or generate power. So if the ultra-low-grade heat, say 60 degrees again, is used to drive the chemical reaction in the desorber. So the ammonia gas is released and it will be absorbed by adsorber at a higher temperature, like 110 degrees, or even higher if a different high temperature source is used in this adsorber. If cooling is needed, then just simply connect two reactors together and the chemical reaction happens spontaneously, as explained earlier. If the ultra-low-grade heat is still used for desorption and making the high temperature, high pressure ammonia passing through an expander turbine, then electric power can be generated. So according to our calculation, with practical consideration taken into account, this picture shows the round-trip efficiency of electric energy storage, which is defined the ratio of the discharged electricity to the charged electricity. The calcium chloride strontium bromide cycle and the manganese chloride calcium chloride cycle can achieve round-trip efficiency higher than 100% when the heat source temperature is higher than 50 degrees and 60 degrees respectively. And if the upgraded heat is preferred rather than the power generation, the temperature lift can be around 25 degrees and 45 degrees for these two cycles respectively. And the manganese chloride sodium bromide cycle has very low round-trip efficiency, but it can achieve around 75 degree temperature lift. The thermal efficiency of upgrading heat is around 0.3 to 0.5. The thermal efficiency of refrigeration is around 0.6 to 0.75 for refrigeration at 0 degree. And more results, discussion, and detailed analysis can be found in our publications. And this photo is our laboratory test rig for thermochemical sorption storage system. We have a compressor expander in place to be installed later for comprehensive tests of hybrid storage system. We also developed a commercial prototype through an Innovate UK project, which is being manufactured at the moment. And that's basically what I would like to share with everyone today. Thank you.
Thank you very much, Huashan. Again, please, if there's any questions that you have, put them in the chat and we will cover them in the Q&A session at the end. Our next speaker is Zhiwei Ma. He's an assistant professor at Durham Energy Institute. His presentation is going to be on seasonal solar thermal energy storage. Zhiwei is as I said, assistant professor at, in the Department of Engineering at Durham University. He also received his PhD in the Institute of Refrigeration and Cryogenics at Shanghai Jiao Tong University. He worked as a research associate in the Department of Materials Science and Engineering at Sheffield University before joining the Sir Joseph Swan Centre for Energy Research in Newcastle, and then joined Durham University in 2019, I think. His main research is around thermal energy storage, low-grade heat utilization, and novel thermodynamic cycles for heating, cooling, dehumidification, and power generation. In 2019, he was awarded the prestigious award of the Sade Carnot Award by the International Institute of Refrigeration for his contribution to low-grade heat utilization. So, Zhiwei, it's over to you.
Thank you, Tony. I'm going to share my screen first. Good morning. Today I'm going to say something about seasonal solar thermal energy storage. I'm going to say something, briefly introduce seasonal solar thermal energy storage and introduce some pilot projects using water as storage material. And the third section is about the water sorption heat storage, which is a hot topic. And the last section is about our research in Durham, in our group, using sodium acetate trihydride to do seasonal storage. So we all know that there are seasonal mismatch of solar energy and heating demand. We have a lot of solar energy in the summer, but we don't need heating. So there's a surplus here. If we can store this heat for long term, like 3 months, 4 months, and reuse them in the winter time, we can achieve solar heating for the whole year. That will increase our renewable heating. I show you a table here to have a look how much heat you can have, which is useful heat from 20 square meter flat plate collector facing south on the roof. So assume you have 50-degree inlet water temperature, which is enough to do some heating. I list 8 cities across the UK. You can see the figure here. We can have useful heat between 4,200 kilowatt hour to 6,500 kilowatt hour. This number is almost enough for a typical UK house with 100 square meter floor area and with very good insulation. So let's have the key question is how we can do the storage for long term. Actually, all these technologies like sensible heat storage, latent heat storage, and thermochemical storage, as Huashan just mentioned, can do the long-term storage. So the key question is the energy density and the volume you need to store the heat. You don't want another house to store the heat for your house. So have a look at the table here. If you're using water, the energy density is quite low. You need more than 140 cubic meter to store 5,000 kilowatt hour heat. And paraffin, of course, higher energy density, a low volume. And if you use sorption technology, like zeolite water and some salt water and some salt with ammonia, you can have higher energy density and a lower volume. And the minimum value we have here is strontium chloride and ammonia, which give you no more than 20 cubic meter storage volume. So that's solar thermal energy storage. So in the second part is some pilot projects using water as storage material, which was delivered in Germany. I think it's 20 or 25 years ago. They started to do some pilot projects using this concept. So you can see here in the picture, they built a giant tank with the volume of 5,700 cubic meter. That's one is in Munich in the year of 2007. Coupling with 2,900 square meter solar collectors. And this system was served for 24,800 square meter heated area. So that's a kind of a central heating system using this solar collector and storage systems. Due to their calculation, this system can cover 47% of the heating of the whole year using solar heat. You can see their site plan here. The red color, that's the solar collectors on the roof of the buildings, and there are pipes linked to the central heating plant and the storage. And in the central heating plant, they have some heat exchangers, and in some projects, they use heat pump to boost the temperature to higher level for storage and also for the discharging process. Here is some summary of the different projects at different level, different storage volume, using different storage method, like above ground tank, underground pit, and underground borehole and aquifer. You can see the summary here. This is the cost, the investment cost per cubic meter water storage. Of course, the specific cost reduced with increased volume. And for a 10,000 cubic meter storage volume, you can see the cost is around €100 per cubic meter water storage. That's the summary. I think it's 10 years ago. The cost may change now, but that's the only resource about investment cost I found. So that's the water sorption storage is a very hot topic in recent years because it has higher energy density and minimum heat loss during the storage, as Huashan just mentioned. So the water sorption actually has two different type systems, closed system and open system. The closed system, you can see here, that's the same configuration as Huashan just mentioned. We have a reactor here and condenser evaporator here. During the charging process, you give heat to the reactor, and the salt or the sorbent material inside the reactor will dissolve the water vapor and then be condensed here. During discharging process, it gives some ambient heat to the evaporator. So the water inside will be evaporated, become vapor, being adsorbed in the reactor, deliver some heating. Actually, we can use an open system because there are water moisture in the air. So in the charging process, normally we use dry, hot air as the energy carrier, passing through that sorbents to dissolve the water moisture from the sorbent, and the air become wet but warm air. That's the charging process. During the discharging process, we use cold but wet air penetrating through the sorbent bed, and water moisture in the air will be adsorbed by the sorbent and deliver some dry and warm air for the heating process. And there are two different types of materials can do water sorption. A physical sorption material like silica gel, zeolite, activated carbon, activated aluminum. And also there are chemical sorption material like calcium chloride, magnesium chloride, lithium chloride, and strontium bromide. There are some demonstration project, not big scale, just lab scale demonstrator. This project is a European project in the year of 2006. They used 200 kilo silica gel. The heat source temperature is 90 degree and heat released at 40 to 70 degree. The only thing is that this design and this system has very low energy density. The material energy density is only 50 kilowatt hour per cubic meter, and the system energy density is only 33. This is just the first trial of such kind of a technology. They didn't design the system very well. Also, the zeolite, which is another typical desiccant material, was used to do sorption storage. This project is in the year of 2006. This is the open system, so air is used to blow through this zeolite material. The heat source temperature is very high because zeolite they require typically 180 degrees to do the regeneration. Otherwise, there are still a lot of water moisture remain inside the zeolite. And the heat released temperature is around 40 degrees. So, but the benefits of using zeolite is that your process will be very stable, and energy density is high. Material energy density is around 160 kilowatt hour per cubic meter, and system energy density is around 120 kilowatt hour per cubic meter. So besides physical sorption process, the chemical sorption process was also used for water sorption storage, like strontium bromide. The example here in 2014, they used 400 kilogram strontium bromide. You can see the white salt was packed in this trash, and different layer of the trash allow that the air blow through these materials layer by layer. The heat source temperature is only 80 degrees. The energy density is very high because it's a chemical reaction. So material energy density is nearly 400 kilowatt hour per cubic meter, and the system energy density is more than 200. The only drawback for this kind of salt-based water sorption is the heat release temperature for strontium bromide is only 25 to 32 degrees. So if you use this kind of technology, you need to couple this technology with some low temperature heating facility, like a fan coil, like underfloor heating. It's a summary of this kind of water sorption heat storage technology. The horizontal coordination, that's desorption temperature, and the vertical coordination, that's energy density. You can see a lot of projects use zeolite because it had very stable performance. And the only drawback is that the desorption temperature is very high. Of course, you can use silica gel, which is cheap, and the desorption temperature is only 80 degrees, but the energy density is low. The chemical sorption material like strontium bromide, magnesium chloride, and lithium chloride generally has higher energy density, but using salt have other issues like they are generally corrosive, and that cannot be used under relative humidity because the salt will absorb water moisture in the air and become liquid. So there are some study of using composite material to do the water sorption. And the last section I want to say is about our study in our group, which is using a kind of a salt hydride, a sodium acetate trihydride, a short name SAT, to do long-term storage. This SAT at room temperature, that's a white crystal salt like this. And if you heat this salt at 80 degrees, it becomes a transparent liquid, just like water. And this material has very large supercooling degree, which means it needs very low temperature to freeze to get it back to solid state. Although this phase change temperature is 58 degrees, it will not turn back to solid, let's say at until let's say minus 10 degrees. That's because it has very large supercooling degree. So you can store this material at ambient condition without any insulation for long term. After seasonal storage, the temperature of this liquid drops to the ambient temperature, let's say 5 degrees or 0 degrees, but it is still liquid. So if you give some activation, like using coat finger, like seeding and a supersonic treatment, you can manually control the solidification process. You can activate the solidification process by yourself. Just like I'll show you a GRF here. You press this clicker inside this bag, it will induce the freezing process. So this process releases the heat. That's the mechanism behind this storage process. And I'll show you the energy change process during the storage and energy discharge process here in the figure. So that's the enthalpy in the vertical coordination. So after charging process, the material turns to liquid at higher temperature, let's say 80 degrees at point 1 here. So if you store that at ambient condition without any insulation, the temperature will reduce to 0.2 and the enthalpy will reduce to 0.2 here. So after that, because the large supercooling degree, it will not follow the solid and black curve, which is the equilibrium enthalpy line, but follow this dash and blue curve to point A here, which is at ambient temperature at 10 degrees. So from 1 to 2 to A, you lost some sensible heat because there is no insulation, but the latent heat, the phase change, is still remain inside the liquid. So at point A, you give some activation and induce the phase change. The solidification happens. The temperature of the material increase to the phase change temperature, which is around 56, 57 degrees immediately from A to B, and then follow the solid equilibrium enthalpy change. So 1, 2, A, that's the storage process, and A, B, and C, that's the heat release process. You can see here, even without any insulation, the charging heat, 50% of the charging heat, it still remain inside the material. That's because of supercooling. So we built a model to do the simulation of this process, just a simple single tube model with material stored inside the tube and heat transfer fluid goes at outside the tube, and the solidification starts from the top. So it's like the white solid will grow through the top to the bottom. So this is one of the results here. You can see the black curve, that's the temperature of the material, increase to 57, 56 degrees at the first minutes and decrease gradually. And the heat transfer fluid temperature, the inlet temperature is 10 degrees. And because the heating from the material, the heat transfer outlet temperature can increase to, which is the pink curve, 35 degrees. Of course, we can increase this temperature by reducing the flow rate. So this is the major result here, which is the energy density, which is very important to the storage, of the long-term storage. So the horizontal coordination, that's a storage and the temperature, which is dependent on your insulation, the thermal insulation conditions. For perfect storage, let's say the storage and the temperature is at 80 degrees. If you're using water as the storage material, you will have energy density around 70 kilowatt hour per cubic meter. But if you use SAT material at the end of the storage, if you have perfect storage, perfect insulation condition, you will have 140 kilowatt hour per cubic meter storage density. Even we have no insulation and the material temperature drops to, let's say, 5 degrees here, you still have 60 kilowatt hour per cubic meter energy density. That's saying that even without any insulation, using SIT material will have the similar level of energy density as water storage material, having the perfect insulation conditions. And because the simpler system, the system energy density is not much lower than the material energy density. So for the system density, even though there's no insulation, we still have like 50 kilowatt hour per cubic meter energy density. So the advantages of using such material is that you have larger energy density comparing to water storage and a simpler system comparing to the sorption storage. And these are advantages. The output temperature is limited to the phase change temperature, which is 58 degrees. And there is a risk of self-solidification, which is out of your control. You need some careful design and cleaning of the system. Okay, that's all the presentation I want to talk. Thank you.
Okay, thank you, Zhiwei. Again, any questions that you have, please put them in the chat. Our next speaker is Dr. Charlotte Adams. Charlotte is a commercial manager at the Coal Authority, working on commercialization of geothermal energy from abandoned mines and other mine-related innovation projects. Charlotte originally trained as a hydrogeologist and worked at Durham University before being appointed to her current role. She's also worked previously on in the renewable energy sector. She's going to present on heat storage within our mining heritage. Over to you, Charlotte.
Thank you, Tony. Okay, is it still there?
Yeah, it's fine.
Great. Okay. Thank you to Tony for that introduction, and also to Jackie and the Heat Hub for the invitation to speak this morning. Tony's given you some information on my background and current role, so that's saved me a bit of a job now. It's just to say that the material I'll be presenting this morning is very much at an idea stage for us. So these are just some concepts that we're exploring as to how we can use the subsurface infrastructure that we have for thermal storage. So we very much welcome collaboration and ideas on this. If you aren't aware of the Coal Authority, our sponsoring department is the Department for Business, Energy and Industrial Strategy, or BEIS. We're a non-departmental government body which was created in the 1994 Coal Act. And across the UK, there are around about 23,000 abandoned deep coal mines, and we effectively own that infrastructure. And also the coal fields underlie many of our major towns and cities. And that's not surprising because many of them were created from the wealth that was generated by the coal that was beneath them. So the point being there that we have good correlation between where the areas of resource lie in the coal fields and where the areas of demand for heat lie. So in terms of what we do, our role is very much geared towards the protection of both people and the environment. So in order to fulfill that role, we effectively deal with things like ground stability and water emergencies. So we deal with any kind of liabilities left over from the mining era. So after mines are closed and pumps have been turned off, water levels may rise within coal fields and they may emerge at surface. So in that case, we would install measures to pump water and treat it to avoid any kind of pollution incidents, both to surface water courses and to underground water supply aquifers. And we have around about 75 treatment schemes across the UK where we pump water and treat it if we need to. And we see those very much as hotspots for delivering mine energy because we have around about 100 megawatts of heat there, which is currently going to atmosphere. one of those at the moment will form the basis of a new heat network planned at Seaham Garden Village. So in terms of what's happened to the UK coal industry and the kind of legacy that we inherit, we've had over 300 years of mining, deep mining this is, and this ended in 2015 with the closure of Kellingley Colliery in North Yorkshire, which was formerly there to supply a nearby power plant, which is also no longer functioning. And you can see from the graph there that coal output over the years was shaped by both political events such as wars and strikes, and also changes in technology. So switching from steam to diesel and electric trains, cheaper imports of coal from other countries, the dash for gas. So these things ultimately led to the decline of production. And then also you've got on top of that the kind of decarbonisation agenda. So with coal very much being phased out of our energy mix, as demonstrated in June when we had 2 months without coal generation, which was the longest time that had been achieved since 1882. So we have this legacy of underground shafts and galleries. We have water coming out at surface that we treat, and we produce materials from the treatment of the water. So we're very much trying to repurpose the legacy. In terms of the water, the amount that we treat per annum is equivalent to the daily water demand for about 2 million people over the same period. And the Environment Agency predict that there will be a shortfall in water within 25 years. So we're exploring whether some of the water that we produce could form some or meet some of the demands. And as part of the treatment systems, you can see in the picture at the bottom, there's this orange coloration there. So that's effectively what's produced in our treatment systems. The biggest thing we deal with is iron. So we get it out of solution by oxidizing it in our treatment systems. And we also have a market for that. So it's used as a soil improver and as a pigment. And also it's very good at absorbing things. So it's used for water treatment as well. So we have markets for our ochre, and we're exploring markets for water. And also what I've talked about previously in some of these meetings, mine energy is something we're looking at. Obviously today we're going to be more focused on the storage. So just a brief background of what we are doing with the mine energy. We estimate that there's enough heat in the coal field to heat all of the buildings that overlie it. And the reason that it's attractive to us is obviously we have the access to it through the infrastructure that we own. But we think it's a good source of heat because we don't have any seasonal variation in the source temperature. So if you've got a heat pump system running on a mine energy system, your coefficient of performance will stay constant, unlike an air source heat pump or a surface water source heat pump, where the COP tends to drop when you need the heat most. And if you compare this to open loop aquifer heat pump systems, which again are similar in that they have a constant source temperature like the mine energy does. The reason mine energy has benefits over that type of system is because the structures that we target underground are large open structures capable of flowing much greater quantities of water. It means you can get away with fewer boreholes to access it. And we also, because we tend to take the water from one seam and put it back in another, we find that the boreholes can be quite close together on surface sometimes, so that's quite good if you've got a constrained site. And this diagram is a simplification of how it all works in practice. If we were doing a larger, maybe 2 or 3+ megawatt size scheme, we'd probably have a couple of boreholes for abstracting the water and one for re-injecting it, just to give you a bit more flexibility and resilience on the system. So in terms of storage, we're thinking about the bigger systems. So we've got 30 or so mine energy projects coming along in a pipeline. We've got 2 or 3 that are actually at development stage. So it's a really exciting time for us. And in terms of building this into the kind of bigger system, we're thinking about how we could integrate other energy sources and demands. So for example, we could use renewables. So thinking about maybe power to X, where X becomes heat, and you would store surplus electricity within the mines as heat to help with grid balancing. You could also use waste heat. So we're thinking about maybe energy from waste plants. And then also you can use the mines for cooling, so you can reject heat to the mines as well. So there's quite a few opportunities we see there. Just thinking about the kind of waste heat and cooling demands, we have to think about the transiency of those. Opportunities might not always be there, so that's something to think about if it's part of a heat supply network. But basically what we're thinking of doing is, how can we raise the temperature in the mine shafts and the workings by using some of these other sources that I've just described? And the benefits of doing that are, having near or zero carbon heat provision, grid balancing, as I've already mentioned, storing surplus electricity as heat. It allows things like energy from waste plants, which might have an overproduction of heat, to prioritize electricity input when they need to, because they then have a source for the heat that's being produced as well. We see some technical challenges. As I've mentioned, this is very much as at ideas stage for us, but that also presents opportunities for the supply chain to meet those challenges and develop products and systems that would work alongside this. And then, similar to the basic mine energy systems that we're looking at, there's also local benefits for supplying clean energy, energy spend being retained within the region, and things like improvements in local air quality as well. So we see lots of benefits to this. And the type of structures that we're looking at, so we're looking at both mine shafts and the underground workings as kind of separate opportunities in which we could store heat. So in terms of mine shafts, of those 177,000 mine entries, we reckon around about 134,000 of those are shafts. So the map I've got up at the top just gives you a rough idea of the Gateshead area in the northeast. And you can see there all those red dots or crosses on there are all shafts. So in areas that have been mined, we often find quite a high density of shafts. But the thing about them is very often they were, as part of the colliery abandonment, they're very often filled. So they're not all accessible. So one thing we look at if we're looking at a new site is we look for the shafts, and we've got a database to see whether the shafts are usable or not, because obviously that can save you some drilling costs if you're thinking of mine energy system, and also for storage, then we need a shaft that's got a good volume of water and that we can use to reject heat too. And being tall and slender, the mine shafts have good thermodynamic performance. And we do find that some of the shafts that we look at for kind of operational reasons, we do camera surveys, which you can see an example of at the bottom. We do water quality surveys going down the shaft and temperature surveys. We do find that some of them have temperature stratification in them already. Those that are pumped aren't, because they all tend to get mixed up, but the ones that are not pumped are already stratified. And the things we want to look at are to what extent the ground acts as an accumulator and an insulator. So that's the ground and earth surrounding the shaft. The condition and access of these as well, which is something we're looking at. We've also got to think about insets to the shaft. So that's where the shaft joins the bits of the mine that go along horizontally, and whether there's a potential for heat to be lost along those insets. So would we have to seal them, for example, if we were to use a shaft, and how would we do that? And we also need to think about, if we were to reject heat to one of these systems and use it for storage, how long would it take to kind of charge the system up? And what's its kind of operating parameters going to be? And they're all going to be a bit different because they've all got different capacities as well. And another thing we're thinking about is storing in the mine workings. So this is a plan from a mine in Scotland, and we're looking at areas where we've got discrete blocks of workings that aren't highly connected to other areas of workings, i.e. we've got little pockets of mine workings that we could use to tap into by drilling boreholes to put heat in, and another borehole to remove the heat. That aren't massively connected to other places. And a good example of this is the Heerlen project in the Eastern Netherlands. So there they have a heat network which is based on the 5G concept, so an ambient loop heat network. And it's based on energy exchange. So there's heating and cooling being provided to the buildings there. The idea being that there's not massive changes in temperature difference, but in that instance, the whole mine there is effectively used as a thermal store. It's quite deep. It's around at about 700 meters deep. It sits at about 28 degrees. And the thing with that is that it's not connected extensively to other collieries, so it's effectively a thermal store. That said, the project has been running for about 10 years and has been successful, and they've got to the point now where they need to put other sources in because they've got more loads wanting to connect to it. So the Helan project is a great example, a little bit different to many of ours because our mines in the UK are very well connected. And that was done so that you could basically control water levels regionally and also access coal over wide areas as well. So we have a lot of very well connected collieries. So we need to look at where we've got these discrete pockets, maybe in smaller collieries, that could be suitable and also align with the location of the heat source that we want to put into them. So this is the case study we've been working on with Durham County Council, and hopefully we'll have some academic input from Durham University on this as well. We've been talking about a student project potentially. So where the red arrow is a site at Hawthorne, which is a business park, and there's some existing industrial units there and more planned. There's other heat loads nearby. There's the town of Merton to the north. There's the kind of shopping, Dalton Park Shopping Centre, which is also to the north of that. So there's other potential heat network opportunities nearby which are being explored. And the site at Hawthorne, the water levels in the shaft there are controlled by pumping, which is taking place at the coast. So you can see on the map along the coast, there's red dots up at the top and at the bottom of the map. So those are the two places where we pump and currently treat water from. So the opportunities here, we've got a shaft basically that's sort of just under 8 meters in diameter, and it's got a 357 meter water column in it, which we've worked out offers a storage opportunity of around about 17,500 cubic meters. That's already stratified because this one isn't pumped. It's controlled by pumping elsewhere, but it isn't pumped at this site. And we tend to find we've got about 14 degrees at the top of the water column down to 20 at the bottom. And we'd like to look at whether we could do something like, raise the temperatures in the shaft to 40 to 60 degrees. And there's been some research done at a project at Bergmann in Germany that suggests that you could go higher than that as well. But we think that would be quite a good compromise to improve the coefficients of performance of any heat pump system that will be connected. The water depth, the water here is round about 100 meters below surface because we do keep the water levels lower here to protect an overlying aquifer. So we need to think about the electricity consumption in lifting water out of the shaft once we've got heated water in there that we might want to use. But there's an opportunity also to offset that by having some renewables on site. So it could be a very low carbon opportunity here at Hawthorne. And then I just thought I'd kind of put that into context with an above ground thermal storage system. So this is an example that I found in Heidelberg. So this is a large capacity above ground thermal flask effectively. And the Hawthorne shaft is a similar kind of structure, but it's obviously below ground. So we have heard from some consultants that have been involved with heat networks where some of these above ground thermal storage systems are there, that because there's a limit on the height they can be, they're often wider than maybe you would want just to get the capacity, and that isn't quite as good thermodynamically for the kind of stratification and thermal performance. So the way the shafts are configured, generally being slender and taller, makes them really good for storage of heat because you can get that stratification in there. So it's a comparable size, obviously one being above ground, one being below ground. And the thing here, the Heidelberg project was estimated at around about 9 million. And then you've also got things like fewer planning and visual acceptance issues if you're using something that's kind of underground. And we've got to think about the impacts of the ground as an insulator as well. So how well, what's the thermal performance of the below ground system compared to the above ground one. We feel having that insulating effect of the rock around it would be a very positive thing. We need to think about what happens with excess heat. Once we've charged the shaft, does that migrate into the rest of the mine? And if so, can we use that, or is that lost? And then there's also kind of the lifespan. I mean, these shafts have had a long lifespan already, some of them. So, you know, they're structures that are going to be there and accessible for a while. We keep an eye on them in terms of their condition, and the maintenance of them should be minimal going forward. So we believe there's a good opportunity there within them. So we think that we've got some potential to store heat in shafts and workings. And as I've mentioned, it really is at just idea stage for us at the moment, something we'd really like to explore, but we haven't done a lot on it ourselves yet. The opportunities are to provide low and zero carbon heat systems. Grid balancing might be an option. It does improve the business case for a standard mine energy system, because you've got effectively other opportunities there that also have a commercial value to them. And there's the potential to offer kind of local benefits as well. So that's everything from me on that. So thank you very much for listening, and happy to take questions in the chat or at the end.
Okay, thanks very much, Charlotte. So our next speaker is Stephen Thomas. He's founder and director of OGI Groundwater Specialists Limited, based in Durham. He has more than 40 years experience in the groundwater sector. His experience ranges from design of well fields for water resources in a number of countries, to the design and installation of groundwater control systems for various construction projects in the UK, mainly for the water industry, transport projects, and large building projects such as hospitals. So Stephen's going to give his presentation on ground storage of heat, practical applications. Over to you, Stephen.
Today I'm going to be speaking about heat collection, something called defracking, storage and recovery. We're based in the northeast, about 2 miles from the centre of Durham. In my 15-minute presentation, the first thing is all this is based on my own personal experience in being a businessman. I've run OGI for 30 years, about buying land, building a land, choosing the heating system, installing a ground source system, and then taking that experience and turning it into a commercial organization, and probably having had more failures than anybody else that's presented so far in terms of realizing the practicalities of installing this in practice. There's 3 key sections. I want to run through again a heat pump system, because this is critical with providing heat of a sufficient temperature for a building. I'll then talk about road energy collection, but you can consider this as really low-grade heat, and how cheap low-grade heat and how easy it is to recharge the ground. And then finally, what are the opportunities for a mining heritage such as Durham? And I will introduce something called defracking, which we've developed here. These are our offices in Netherfield, which we built around between 11 and 12 years ago. This is one of the rooms with some of my team. And education of heat, minimizing heat, starts here. You can see my scarf at the bottom left, but we keep the temperature at 20-21 degrees. It's very, very comfortable office, modern office. What I'm doing is I'm working backwards. If you're going to lower the carbon footprint, then you start off with having underfloor heating with smaller spacing than you would normally have with a standard system. So you can see here we had about 200 to 300 millimeter spacing between the coils, which means we actually only keep our temperature in our pipes at 30 degrees, 30. So if you're abstracting heat at 0 from the ground, that's only a 30-degree lift, and I'll explain that later. This is that's Dr. Richardson, probably the most overqualified plumber you can consider. Then the pipes are screed, and that's the floor. Right, heat pump, to those that aren't familiar, you have two separate pumping systems. You have the primary pump, which pumps the glycol around your collector pipes, in our case here, out the back, which I'm looking at right now to the window. You pump out at a temperature, you bring it in about 4 or 5 degrees higher, and that flow rate times the temperature times the volumetric heat capacity gives you the energy to the building. Runs through the heat pump, electricity provides to the heat pump, then it outputs on the secondary pump the hotter water that runs to your buffer tank, and the buffer tank then feeds your underfloor heating. So in principle, your building uses the heat, it abstracts heat from the heat pump, sends cold water into the ground, that ground via conduction absorbs heat, and warmer temperature, maybe 4, 5, 6 degrees, goes to the building. Okay, now there's how you collect the water, the heat from outside. This is a project we undertook the design and construction, 100-meter boreholes. You take the borehole, you put in a number of collection pipes. Now these are closed loop pipes. So in this case, we had a double loop system, so 2 loops. Again, the design of the loops, you can get more efficient if you run 2 sets of loops through a borehole. Then you put a tremie pipe and you grout it. I'll talk about the grouting later because this is critical to an opportunity for the northeast. Basically, you put a tremie pipe into the bottom and you put in a mixture of bentonite, high conductivity bentonite to absorb the heat. Then you connect the top of the boreholes to the vertical heat transfer pipes. This one is particularly in Leicester. And you have a flow and return to each borehole. Then you can see the collector pipes. You keep them separate to make sure the heat doesn't connect. So they'll be flow return pipes. They're separated. Finally, they come to a manifold where it's collected. And that manifold you can access from the ground level. There's the connections to the manifold. There are the valves inside the manifold. And it goes to, you can see it to the top of that. That's the large flow and return to the building. Or you can have the manifold inside the building. This past one was in Stanley, Durham. This was in Leicester. And then you get your heat field. So in this case, a series, this is in Cramlington. And you've got your flow and return pipes on this one, slightly different arrangements. But ultimately, what you've created on the right here is a large cool field, and it's attracting heat from the surrounding ground. This is a closed loop system, okay? And then you design it so it's sustainable and it feeds the building. So the basic mathematics are that you have energy from the ground, which is, if you like, free. You've got input electrical energy, and then you've got your energy to the building. So the combined energy from the ground, energy to the building gives you energy to the building. And the ratio of energy to the building divided by electrical energy is your COP, which Charlotte's mentioned there. So our heat pump is a Wiesmann, and this is from their website, this is from their charts, and basically, as a standard, they say if your brine or glycol temperature comes in at 0 degrees and you're outputting at 45 degrees, you can expect a COP of 3.5, which is about 25 to 30% from electricity, 70 to 75% from the ground. So if you're using X number of kilowatt hours, you have to provide 25, 30% from electricity. So it's a good multiplier, but not fantastic. So the question I have here for this seminar is what if you preheated that ground to somewhere between 25 and 30 degrees, which we have done. We've done in practice on our projects. And then you design your internal system so you've only got to output at 35 degrees with close spacing for heating. How would this improve the efficiency of the system? Right, next stage is one method that you can consider collecting very inexpensively heat. So we've applied at one of our sites what's called a road energy system. And in a sense, it's the opposite of underfloor heating. You put more hard-wearing pipes in a racking and you surround it with asphalt. That asphalt then attracts vast quantities of heat over the year, not just in summer, but in winter too. We've calculated in the order of 200 kilowatt hours per square meter per annum, which when you've got to build a road anyway, that's a massive amount of heat that's available, which is currently just going to waste. So the principle is you use the same ground loops, you collect the road energy, but via a separate loop system. It goes through a heat exchanger and then you dump that heat into the ground. And we have measured increase in the ground in the northeast between 25 and 30 degrees, which means that if you need the temperature in your building at 35 degrees, you're only uplifting the temperature between 5 to 10 degrees. So it has a huge, very little electricity to boost that up. So as an example, road energy systems here, you can see it being laid. There's another example of what we call a hot deck system. You can either put it in racking or you can put it down with this system. But the principle is the same. You put the pipes in the main asphalt. You keep the wearing course above it, so that can be replaced as normal. The installation is very simple. You whack down the type 1 material on the surface. You put a base course on. You then spray it with a what's called a tacker coat, and then you lay in the background is the racking. This took place in one day for laying this top surface. You lay it down over the site, like so. Spray it again, and then it's a two-man job to put in the pipe work. This all goes to, again, another manifold, an external manifold, and then finally it's finished. There's your car park, and you wouldn't know anything's there. But that little car park here effectively provides 80% of the heat to the building. But as one of the earlier speakers mentioned, the main heat you get is from the summer, spring, and autumn months, but you need it in the winter. That is collected through a heat exchanger and then pushed into the ground. And this stays relatively local. So this would be the standard. But when you extend these graphs, you can see that you can increase, which we measured. That COP is 7.5, which means in practice, you only need 13% from electricity and 87% from the ground. So that more than halves the electricity demand. And again, if that electricity is from solar panel or wind turbine, then you have a zero carbon usage. That's the principle. Very simple abstraction from heat from the road, but it could also be from waste heat from refrigeration units, for example, in a Tesco's. There's an enormous amount of waste heat. We've captured heat from solar panels that have to vent because they're too hot. I mean, there is a vast quantity of waste heat up to 25, 30 degrees that can be dumped in the ground, and the ground is very absorbent, will absorb it very easily. Finally, what are the particular opportunities for a mining heritage such as Durham? Well, this is why I wanted to build up on Charlotte's talk, is that we've had experience of putting closed loop boreholes in a mining environment. Most of them are very challenging. The first one, occasionally go into mines and we have to block them up. But you saw us putting the boreholes in with the grout. We delivered, I calculated the grout requirement for a 20 borehole system, sent it to site. And at the end of the day, my operator rang me back and said, that first borehole was brilliant. When's the rest of the grout coming? What had happened is that we hadn't hit the mine, but we stopped 20 meters short. But what we discovered is that the abandoned mines, many collapsed, and the ground above the mines, maybe for 100, 150 meters, were like an accordion expanding, and it effectively fractured, produces numerous horizontal fractures. And of course, our grout had disappeared into one of these fractures and was lost. But later on, we found out that it was an incredibly efficient borehole, producing about 4 or 5 times more heat than a standard borehole. And it's because the high conductivity heat had sort of fingered its way out from that. So whilst our borehole drilling was only 300 millimeters, it was effectively like having a 3-meter borehole for heat collection. So we call this process then defracking, because we are not only making use of those fractures to bring the heat in, but the grouting process stabilizes that ground as well. So this is the concept of the mines. Our process is that we drill, but not into the mines, above the mines. And then stage 1, drilling. Stage 2, abstraction and trimming in the high conductivity grout, putting in the loops, and then again that goes to the heat pump. And in the northeast, it's fantastic because one borehole produces the equivalent of about 3 normal boreholes where it's non-fractured. So our vision for this is a system whereby you can combine houses, road energy, collection pipes, but the individual has a heat pump, but there is an independent supply of the charged glycol. So that can be done by a third party, and that works very efficient, leaving you with, again, a community which feeds off the mine heritage. Thank you. Oh, two projects, local projects, excellent projects, Primary Care Centre Stanley, which we did, and Lanchester Road Hospital as 2 examples where we used this defracking technique. Thank you.
Okay. Thank you very much, Stephen. We come to our final presentation. It's by Lukas Bergmann. Lukas is residential HVAC product manager for Sunamp and has previously worked in heat pump research and heat pump market research and development across Europe. Lukas is going to present on Sunamp heat batteries. Over to you.
Thanks for the introduction, Anthony. My name is Lukas Bergmann. I'm product manager at Sunamp Limited. And my presentation today is about PCM heat batteries and why they will revolutionize thermal storage and enable the decarbonization of heat in the UK, but also globally. Before I start with the main part of my presentation, just a few words about Sunamp itself. Sunamp is a company that has been founded in 2006, and we produce heat batteries to store both heat and cold energy. Our heat batteries are available in a range of different sizes, from residential to commercial and industrial scale. They have an outstanding thermal performance and very good insulation levels, and they have an outstanding material performance of the material inside the heat batteries, to which I will come a little bit later. And most importantly, they are the most compact thermal storage that are on the market today. Now, what that looks like, you can see on this picture here, which is from our experience room. On the left-hand side, you see a standard 210-liter unvented cylinder, as they are being sold today in the UK. On the right-hand side, you see our heat battery, a Unique 9, that delivers an equivalent amount of hot water to the building, but in a quarter, roughly a third to a quarter of the space. The benefits of heat batteries are not only that they provide mains pressure hot water and high flow rates and reduce the space requirements, but they also save costs through lower heat losses, don't require pressure and temperature relief valves. For those of you who are from the installer and plumbing trade, that will probably mean something. You also don't need the associated discharge pipe work. They can be sited very flexibly because of that, are easier to install, and they have no maintenance requirement and have a 10-year warranty, including on the internal heating element, which is something that's unique in the market. In terms of the agenda of my presentation, I want to first of all talk a little bit about what a PCM heat battery actually is. I'm going to make a very brief excursion into what PCMs are, mainly because we've heard about that already quite a lot in the first two presentations. And then I will talk about why they will become a key part of the energy transition in the UK towards a decarbonized heating system. So, what is a heat battery? There are, I think, several definitions of this out there. Our definition of a heat battery is that they are thermal stores storing energy from various sources and providing it as useful heat or cold energy using phase change materials. So if we look at this in a little bit more detail and deconstruct the content of this, first of all, heat batteries are thermal stores. What that means is that they do not store the medium that you actually want to use the heat in. So they do not store potable water or system water that is to be circulated through the heating system or comes out of your tap or your showers. They use another material to store the energy that is required to heat the actual distribution medium. Secondly, they can accept energy from various sources. What that means in our case is that we can heat our heat batteries directly from electricity, through an internal element, but we can also accept heat from, for example, heat pumps, but if necessary, also from boilers. We work with heat networks and other heat sources too. They provide that energy that is being stored as useful heat or cold energy. Our main material and our main product that is on the market, available on the market for public sale today, is focused on heat storage. It provides heat at a useful level for space heating and hot water provision. But we are also for one-off sales and in projects already offering materials at lower temperature levels to store heat at temperatures that are useful for refrigeration, cooling, and also beyond the useful temperature levels for space heating. And last but not least, our heat batteries use phase change materials. We've already heard quite a bit this morning about the use of phase change materials and their benefits. And I just want to very briefly recap that. So our heat batteries use latent heat from the transition of a material from its solid to its liquid state. Probably the most well-known example of that that everybody has come across already is water. Water at a temperature of 0 degrees changes from its liquid to its solid state and vice versa, depending on whether temperatures or whether energy is taken out or put into the system. Now, the important and interesting point is that the amount of energy required to turn 1 kilogram of ice into 1 kilogram of water is the same amount of energy that is required to heat that kilogram of water from 0.1 degrees to a temperature of 80 degrees Celsius. So as you can see, in that process of turning from a solid to a liquid, there's an enormous amount of energy stored in this case. But obviously, for water, this is not at a temperature that is useful to us when what we want to do is provide space heating. At Sunamp, we use a different material that's already been mentioned today in the second presentation. We use a material that is well known from these little systems, hand warmers. I've got one here. It's sodium acetate trihydrate, SAT, and we have made several changes to the formulation to make it suitable for use in space heating and hot water applications. Sodium acetate trihydrate provides about a fourfold increase in terms of energy density, which means that the products that are using it can be about four times smaller. In reality, a little bit less than 4 times smaller than hot water tanks. Sodium acetate trihydrate, I will just show you. As you can see, it's now freezing. And unfortunately, I do not have, laptop cameras are not thermal imaging cameras, so I can't show you that. This is now at a very nice temperature that will keep my hands warm and or could deliver me hot water for showering and other purposes. Now, one thing that is important to mention when it comes to phase change materials and latent heat is that this is not at all a new concept. In reality, the discovery of latent heat goes back to Joseph Black, who discovered this while still a professor at the University of Glasgow back in the 18th century. And he discovered the fact that the temperature in an ice-water mixture does not change, while the temperature in a cold water mixture does change over time. In the 1940s and 50s, Maria Talkes in the US then tried to use the concept of latent heat for the first time to provide space heating for homes. She was the developer of the Dover Sun House and very successfully actually used solar thermal energy to charge a large bank of phase change material, which you can see here in the middle, and provide space heating for the house over the year. Unfortunately, and this is one of the main reasons why phase change materials have not been in use successfully until recently, unfortunately, after the third year of operation, the phase change material that she was using started to separate and lose its phase change material properties. So what Sunamp has done is that we have been working very hard since 2006, since the foundation, for about 7 years, mainly on researching phase change materials and developing a solution to the stability of the product. We have achieved the only product in the world labeled as a grade A product by the RAL PCM quality mark. What that means is that our products have been tested to more than 10,000 cycles of charge and discharge. Unfortunately, that's the end of RAL's scale because they have never had anything that was able to go beyond that level. In reality, we have tested the material on our own benches for more than 40,000 cycles, which on a 2 cycles per day basis would deliver you about 50 years of useful life for the material. Now, I want to talk a bit about why thermal batteries or heat batteries and thermal storage are going to be a key for transitioning to a decarbonized energy system in the UK, especially in the heating sector. First of all, one of the points that I want to highlight is how we are going to heat our homes in the future. The recently published 6th carbon budget of the Committee on Climate Change highlights that in their balanced net zero pathway, and actually in all other pathways that they have modeled as well, a huge amount of heat pumps is going to be required to heat our homes sustainably going forward. The net balanced scenario estimates that more than 25 million homes will be heated by heat pumps 2050. That brings with it a lot of challenges. First of all, around the deployment of these systems, the supply chain in the UK currently is still, let's say, nascent. It brings some challenges with it in terms of costs, because heat pumps today are still significantly more expensive than the main competitor, which is a gas boiler. But one thing that is often very little talked about is that it also brings with it some challenges regarding space, and in particular space inside homes for hot water storage purposes. And I will address this in a moment. The second point is that consumers in the UK have come to expect a way to heat their homes, which is essentially not very well suited to the operational parameters of heat pumps. We tend to heat our homes for very short bursts in the morning, switch the heating off during the day, and then put the heating on again in the evening. What this leads to is a demand profile, which you can see here, which is a zoomed in section of a very famous chart, I think, in energy policy circles, which I'm going to show in a moment as well. Thirdly, we need to make sure that the transition to sustainable and decarbonized heating is the customers and the end users with higher heating costs than before. And one of the key drivers for this, other than moving subsidy costs, etc., from the clean energy, which is electricity, to the dirty energy, which is natural gas, will be the use of flexible tariffs going forward. And last but not least, this chart here has been used and misused quite a lot over the last 10 or so years. This is from a doctor thesis from Robert Sansom, which was published eventually, I think, in 2014, and which shows a half-hourly heat demand profile. And this has very often been used to say, oh, but look at how high the energy demand is for heating, and how small the electricity supply is in comparison. And it's absolutely impossible to achieve this going forward. But as you can see, if you look at a zoomed in version of this, these extreme spikes that you can see in the graph here, and which look very solid, and because it's a full year and half-hourly steps, actually there's a lot of room in between them, and this is going to be an important part of what I'm going to talk about. So what does how do heat batteries and thermal storage come into play here? One very important point to make is that heat batteries can be used to deploy heat pumps successfully in applications where previously this would have been impossible. They enable thermal storage in the smallest of spaces because of their higher energy density. And I want to use a real-life example of what that looks like. This is a project that is not too far away from Durham. It's in Sunderland. It's called Core 364. If you want more information about the project, there's a very good video that explains some of the backgrounds, and you will find a link in the presentation after this. The Core 364 project has taken 7 tower blocks in Sunderland with a total of 364 apartments and 364 combi boilers, and removed those combi boilers from the apartments and replaced them with individual small heat pumps connected to a shared ground loop system. Prior to the installation of this new system, the towers were emitting about 600 tons of CO2 per year. There was a very high fire risk, which of course, due to the tragedy in Grenfell, had become extremely high on the agenda, or has become extremely high on the agenda for all property owners of these types of buildings. And they were also being faced with very high maintenance costs. Now, what was done in this case, and really here the heat batteries were the enabling factor, was to, while all the residents were still inside the building, introduce a shared ground loop system, and then from the top of the building downwards, start removing the gas boilers and connect the flats to the ground source heat pump system. Why were heat batteries central in this? Because of the way this has been done, and because they couldn't essentially remove the tenants for the duration of the project, they had to keep the whole system operational. So both the flats already connected to ground source and the flats still connected to gas had to be operational at the same time. Therefore, they were not able to remove the gas infrastructure from this area of the flats, and had no space to fit a hot water tank that is a requirement with any heat pump today to provide hot water storage. So The other option then was to use this space back here in another cupboard. But the challenge here was that this is such a small cupboard that none other product than the heat batteries would have fit inside there and provided sufficient heat storage. The project has completed successfully. There's been delays this year, obviously, because of the COVID situation, but it has been completed successfully, and it's bringing 70% CO2 emission reductions, and they are further reducing, of course, because of the continuous decarbonization of our electricity supply. A greatly reduced fire risk, no Legionella risk, because we do not store large quantities of water inside our hot water tank, a very low maintenance, no billing issues, and no decanting. No billing issues is a very important point because essentially every flat has its own electricity meter, and because we have individual heat pumps, the billing is very, very much simplified compared to standard communal heating systems. Another point where heat batteries will be able to greatly support the deployment of heat pumps in particular going forward is that they decouple the heat demand from the heat supply. As I already mentioned, in the UK, we have come to be used to deliver heating in relatively short bursts, and consumers are expecting a fast reacting system that delivers them heat when they want it. And the problem with that is that heat pumps are not very well suited to deliver this. But if you use thermal storage as an intermediary, you essentially decouple the heat demand from the supply of heat to the heat storage. So while the heat storage can be discharged based to the customer's preferences, the heat supply to the thermal storage can be the heat can be supplied to the thermal storage on a very continuous and regular basis, reducing cycling of the heat source and therefore improving the performance of the system. Thirdly, we are rapidly moving into an energy system where the when of energy use will become much more important than the how much when it comes to the costs associated to that energy. The graphic I've shown earlier was the cost profile, and that you also see here in the top left is the cost profile of the Octopus Agile tariff. And as you can see here, there's actually a period with negative costs, which means you get paid when you use energy during that time, and with extremely high costs, the 4 to 7 p.m. period when the grid is kind of at its peak usage. Enabling the use of these types of tariffs requires either an extremely high thermal mass in the building, for example, by having underfloor heating in screed, as in Stephen's example, coupled with very good insulation, or it requires dedicated thermal storage to provide the same system function to the building. Now, one interesting fact is that the energy density of the material, if you use it in a space heating application, is actually even higher compared to water, because the delta T that you're operating on is significantly reduced. And what that means is that what you see here on the left-hand side, which is still a fairly standard-sized airing cupboard, is the equivalent of almost 1,000 liters of hot water storage. The two bottom batteries to provide buffering for space heating, and the top two to provide hot water. Again, this is from a real world case. This is a project in the Highlands where 140 homes have been retrofitted with the system using a high temperature heat pump. And the preliminary results from the project show that that we achieve about 59% reduction in carbon emissions and falling. By the way, 59% is always a little bit misleading here, because this is based on SAP scores, which are not really up to date at the moment. We've also achieved a 55% reduction in running costs and the energy efficiency rating targets that the Housing Association in this case had to achieve with this system. And the last point, and a very important point that I want to come to, is the fact that thermal storage and heat batteries address the supply challenge on a national level. this graph, as I already mentioned, has been used and misused quite a lot in the last 8 to 10 years in the UK's energy debate. What this graph shows is a half-hourly profile of heating demand calculated by Robert Sansom in his doctoral thesis. But because this is a full year in half-hourly steps on a single graph, it looks like there's huge solid blocks of very, very, very high energy demand across the whole year. And obviously, as you can see, it exceeds quite significantly by a factor of 7 in its peak the electricity supply over the same periods. But if you take the data behind this graph, and Andrew Bissell, our CEO, has very kindly been supplied with that in the past, what you see here is that in reality, these extreme peaks are only occurring for relatively short periods each day. And there's huge troughs in between them, during which the demand is significantly lower. So what we've done is, if you take the average demand of heat over a 24-hour period, you see this in the green curve. You already see that the variance in demand is hugely reduced. And if you then assume that this heat is being supplied by a heat pump, and we've used a very, very pessimistic factor in this case of 2.75, just to be essentially on the safe side, you see that actually the additional demand required to supply the heat from heat pumps is within the current range of electricity supply. Obviously, this will still come on top. Also, very important to point out that none of this on this chart takes into account additional energy efficiency measures in the UK building stock. So with that, I'll come to my conclusion. So in summary, heat batteries are here today. They are available today for residential customers through our installer chain or installer network, for projects through direct discussions with us. They will revolutionize how we store heat and cold energy across the globe. And they are an enabling technology for the decarbonization of heat, because they solve the space problem. They deliver what consumers have come to expect. They enable the benefits of flexible tariffs in all homes, and they stabilize the network by enabling large-scale demand response. Okay, that's me. Thanks.
Okay, thank you, Lucas. Okay, unfortunately we've run out of time. I'd just like to thank all of our speakers for their presentations today, and also for all of you to attend this seminar. I hope to see you at our next seminar, which will be in February, and this will be on skills and training for renewable heat revolution. It's just like to wish you all a very quiet and safe Christmas, and fingers crossed for 2021. So thank you very much, and stay safe.
Thank you, everyone.
Thank you.